Okay, so this is a video on special Taylor and Maclaurin series. We're going to add 2 to the list today. We already have 2. So we want to recall that first, if I take 1 over 1 minus x, this is the same as the sum from n equals 0 to infinity of x to the n. But that's only good when x is between -1 and 1. So this is like the place where the geometric and the power series kind of run into each other. The other one that we've seen is that if I have e to the x, this is the same as the sum from n equals 0 to infinity of x to the n over n factorial. And this happens to be good for all real numbers. So no matter what I put in for x, this is going to hold. Okay, so we're going to add 2 to the list today. We're going to add the sine and the cosine. And this is going to complete the 4 special Taylor and Maclaurin series that you're going to need to have memorized for the BC exam. Okay, so let's start building derivatives for the sine. So if f of x is the sine of x, then f prime of x will be the cosine. The second derivative is the negative sine. The third derivative is the negative cosine. The fourth derivative takes me back to the sine, and then we start going around this loop again, right? So this just keeps going on and on and on. So the same thing is going to happen with these values at 0. So we're working with a Maclaurin series here, so we're centering at 0, right? So if f of 0, so the sine of 0 is 0, the cosine f prime of 0, the cosine of 0 is 1. The negative sine of 0 is still 0. The negative cosine of 0 is going to be -1. And then we go around all of this again, right? We're back at 0. And then we're back at 1. Okay, so let's actually build the series that comes out of this. So for a Maclaurin series, we should have f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed plus so forth and so on, right? So f of 0 we found was 0. F prime of 0 is 1, so that's just x. This is also 0. This one is -1, so that's going to be x cubed over 3 factorial. And then we kind of get a pattern going here, right? It's going to be positive x to the 5th over 5 factorial, negative x to the 7th over 7 factorial, and so forth and so on. So if I kind of pair out the non-zeros here, I get x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and the pattern just keeps going. If I write this as a power series, I get n equals 0 to infinity. We need an alternator, so we're going to take -1 to the n. So I want 0 to be positive and 1 to be negative. And then we're going to make our numerator. So let's see, this is going to be x to the 2n plus 1. Right, so 0 gives me 1, 1 gives me 3. That works. And then over 2n plus 1 factorial. So we have this semblance that this, for some values of x, is going to equal the sine of x. I mean, at a bare minimum, it's going to work for x is 0, but because it's a Maclaurin series, but it can work possibly for some other values. We find that out by checking its interval of convergence, and to do that, we use the ratio test. So let's see, when we do the ratio test here, we take the limit as n approaches infinity. And let's see. We have x to the, it's originally 2n plus 1. So if we make the n into an n plus 1, we have to distribute the 2. We're going to get 2n plus 3 over 2n plus 3 factorial. And then we're going to flip the original one, so we're going to get 2n plus 1 factorial over x to the 2n plus 1. Alright, so let's see what happens there. We combine these, and that's going to give me 1 over... Okay, keep two terms of this time, right? 2n plus 3 and 2n plus 2. And then what do we get? We get an absolute value of x squared here. Okay, so let's see. That limit, so I need a limit here still, right? So this is the limit as n approaches infinity of this. When I take that limit, this thing's going to 0, so the whole thing goes to 0. Well, the nice thing here is that's kind of amazing, because 0 is always less than 1. And it's less than 1 for all x. So it doesn't matter what x is, and it will converge. So the unlikely result is that this series always converges. So the sine of x is always equal to the sum from n equals 0 to infinity of -1 to the n, x to the 2n plus 3 over 2n plus 3 factorial. Okay, so remember, this is odd factorials and odd powers, right? Alternating positive, negative. So what we should expect is that what happens for sine should clearly also be very similar for cosine. So let's start that process. Okay, so for cosine, f of x, cosine of x, right? F prime of x, negative sine of x. F double prime of x, negative cosine of x. F triple prime of x is going to be sine of x. The fourth derivative of x is cosine of x, and then we're going around like horning in. So f of 0 is 1. F prime of 0 is now 0. F double prime of 0 will be -1. F triple prime of 0 is 0. The fourth derivative at 0 is 1, so forth and so on. So just like we did with the sine, we're now going to build the series. Alright, so we need f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed, so forth and so on. Okay, so f of 0 in this case is 1. Right, it's just simply 1. Okay, f prime of 0 was 0. F double prime, right, so this is double prime, is -1, so it's going to be negative x squared over 2 factorial plus 0, and then we get the positive x to the 4th over 4 factorial, and then we add another 0, minus x to the 6th over 6 factorial, and this keeps going. Okay, so if we take out the 0 terms, we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. So it's almost exactly like the sine function, but instead of starting at x, it starts at 1. Instead of being the odd exponents and odd factorials, it's the even exponents and the even factorials, and it bounces again, positive, negative, positive, negative. Now, we should expect, and the interval of convergence again should be all r. Let's make sure that that's exactly what happens. So if I write this as a series, n equals 0 to infinity, right? Again, I want the first term to be positive, so that's going to be -1 to the n. Now I have the even powers, so instead of 2n plus 1, I just have 2n over 2n factorial. So we're going to use this series to test with the ratio test. So here we go, employing the ratio test. We take the limit as n approaches infinity. We don't need to deal with the alternator. Let's see. So if I take x to the 2n and then we make n plus 1, that's going to be 2n plus 2 over 2n plus 2 factorial. Right? And we're going to multiply that by 2 to the n factorial. 2n factorial, and then this is going to be x to the 2n. Alright, so simplifying, this is going to give me the limit as n approaches infinity. This is going to again give me two terms, 2n plus 2, 2n plus 1. Everything else is canceled out. And then this is going to be multiplied by, again, x squared. That limit again goes to 0, which is less than 1 for all r. So this tells me that the cosine of x is equal to the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial for all real numbers. All right, so let's summarize our four. Okay, these four series that you have to memorize are actually surprisingly alike. This one just becomes like the natural polynomial terms, 1 plus x squared plus x to the third, so forth and so on. But remember, it's only good on negative 1 to 1. It diverges everywhere else. E to the x was the first one that was a little odd, and that was giving me 1 plus x squared over 2 factorial plus x to the third over 3 factorial. So that's all the terms, and they're all positive, and that's good for all reals. The sine of x was only the odd terms, right? So it starts with a positive, then gives me a negative, then gives me a positive, and then a negative. And that's just the odd terms, but that's good for all reals. And the cosine, right, is just the even terms. So it starts with a positive, moves to a negative, positive, negative, and it just adds up all the even terms, alternating from positive to negative, and that's good for all reals. These four series you need to know. You need to know them because they come up very, very frequently on the BC exam, and you need to know their values without having to do any of this work. Okay, so there you have it. These are the four special Taylor and Maclaurin series that you need to know for the BC exam.